Really excited to be here today. I'm talking about big search with big data principles. So who am I? I run Open Source Connections. We are a Solar Lucene consultancy, been a member of Apache. Contributed a patch to Solr back in 2007 that was a great example of open source at work. 3 different companies all worked on this one patch, constantly contributing it back. And it was the first patch to take binary documents, your Office, your PDFs, and that kind of thing, and extract them. And I like to think that it was sort of the genesis of the Tika project. Obviously, my biggest contribution to the Solr community is working with David Smiley on Apache Solr book. We're currently working on the 4.0 update, so hopefully we'll be done before 4.1 comes out. So what am I doing today? Well, everybody else has probably laid out the, hey, I've got the solution for you. I know how to solve your problems. I've got the exact right answer. That's not what I'm here to do today. I'm here to tell you about a specific big data project that we did search for, and I'm going to tell you about all the good things we did, but I'm also going to tell you about all the bad things we did. So my goal is not to give you sort of the, hey, this is how everything should be done. I'm going to talk a little bit about what we actually did and where things went really well and where things went badly. So, just for those of you, so you're not disappointed, it's not an intro to SolrCloud or Elasticsearch. So we have some great sessions coming up later today about SolrCloud and Elasticsearch. I'm going to be talking about Solr, but I'm actually more talking about lessons and approaches and lessons learned that could be applied to pretty much any search engine. So what's the project I'm working on? Client X, it was a US federal government client. And they had hundreds of millions of documents to be searched. Everything from PDFs to Word documents to text documents to documents in unusual formats that you'd never seen before. They needed to get it all up and searchable, and we had a very aggressive timeline, just a couple of months to get it done. And one of the interesting things about this data set was that all the data had to be searched. There was no option to say, oh, I'm going to do a search query, and if it takes longer than 2 minutes, I'll just kill the query and return whatever I have. The entire corpus had to be indexed, and that also meant that when we indexed 300 million documents, it meant that if we indexed 299 million, and missed just a couple of documents, that was a bad thing. We couldn't go live with that. We had to get every single last document into our index. We didn't have a lot of tools, right? We didn't get to sort of pick whatever we wanted, sort of go out and get best of breed and do everything. We had a pretty limited selection of tools available in this environment. And a lot of this was built on the Solr 3X line. So we did prototype a little bit with SolrCloud, and we're moving to that now. Kind of the genesis of this talk was talking about Solr 3X line. So a lot of the problems or solutions we may talk about, people may say, oh, well, if I just had SolrCloud or if I just used Elasticsearch, there wouldn't be any problems. I don't know that that's totally true. So what was this project? It was a standard boy meets girl story. And for those of you who don't understand that reference, that's like a very traditional classic scenario, right? How many movies are all about a boy meeting a girl, right? How many books and things are about a boy meeting a girl? And in search, I often feel like that classic story is we have content files, some sort of unstructured content data of some sort, whether it's on a file system, a database, wherever. But it's unstructured information. And we have metadata, and we want it, that's got a lot of structure. It's been curated, it's been worked over. And we want to bring them together and put them into a search index, in this case, Solr. So just sort of illustrate, how many people have seen WALL-E? Right? All right, that was a classic, that's a classic boy meets girl story. We have WALL-E on one side, who's got all this great data. And Eve was the robot that got away, and she had all this sort of very fancy metadata. She was from the future. Everything was perfectly curated. And they went through a bunch of adventures to get all the data together. And for us on this project, it was a lot about the ingestion. It was about building the pipeline. It was about making sure we didn't drop a single document. We got all 300 million documents into our index. So... And at the end of it, though, we did get a happy ending. We got all our documents in. We weren't missing anyone, and everything was good. So this is kind of the project. And I think that how many people have done this project? Right? Come on. Yeah. I mean, this is a very common scenario. So what made it interesting was, A, we were doing it at really large scale. We had hundreds of millions of documents that had to be indexed fairly quickly, and we had millions and millions of documents coming in every month. And we used Bash for almost everything. So this was my first my background is a Java developer. I've done some ASP and Microsoft stuff back in the past. I hadn't done really much with Shell or Bash. In this environment, we had a truly phenomenal Bash developer on our team. So we chose Bash, but because it was available, it was everything. And we did a lot of stuff with Bash. We built remote stop and start scripts so we could deploy X number of Solrs out to X number of boxes and start and stop them as we needed them. We had these indexer jobs that we could remotely deploy, and we could start and stop them. We did our performance monitoring, right? It's amazing what you can do with cat and grep and tools like that, looking at your log files to identify where problems are. If we were worried that we were missing a document, we were running the index and we're missing 3 documents. Where did we miss those 3? We used some Bash scripts to go through all our data files and find the missing documents. And then we ran our content extraction scripts with a big sort of Java Tika-based tool that we wrote for pulling out the content out of all those binary documents. And ingestion, again, we ran those scripts from Bash, and then artifact deployment. At some point, though, we realized it was like, wow, we're writing Puppet or Chef. People use Puppet or Chef, right? We're writing Puppet or Chef for managing, deploying all of our stuff, only we're doing it in Bash. So I will freely acknowledge that while Bash was a great solution in the short term, and it got us a lot of productivity, and it got it up and running, we probably rode the Bash train a little too long. And so now we're going back and rewriting some of this functionality more in Java or some other tools that are a little more standards-based. We don't need to reinvent the world like we were doing. There's lots of other great open source things. And so now, with the hindsight, with the lessons that we've learned by doing a lot of prototyping using Bash and the other tools we've had, we've been able to go back out and say, okay, we really want to use, I think we're using Puppet. We really want to use Puppet for configuration management and for deploying things and getting permissions and getting that all stood up. But yeah, definitely don't underestimate the power of using something like Bash to really quickly prototype your environment, because you're going to learn a lot of lessons about the environment that you're working in. One of the things that we quickly realized was the value of a properties file, right? Make it really easy to change things. One of the early revisions of our ingestion script was this big complex XML config file. And it was a nightmare because our Bash scripts couldn't parse XML. Our Java thing, we had pathing problems and everything else. We backed out to a simpler sort of properties file format. And if you notice, we don't have dots between our variables. We have underscores. Why? Because that works better in Bash. But we realized that we weren't going to deploy a single architecture for managing this massive data set. We were going to deploy many of them because we're going to be learning and we're going to be evolving. And so you can see here we've got a bunch of variables about, how many JVMs are we using? How many shards are we putting out there? What ports are everything running, right? We went for very parameter driven because we knew our architecture was going to change frequently. One of the lessons that we learned was on this massive data set, we had to shard all our data, right? Well, then came the question, okay, do we just do sort of traditional sharding like mod 16, mod 64 and equally distribute the documents? Or maybe we want to shard by date time, right? Maybe we want to, put the more recent documents on one shard and then the older documents on another shard, and then maybe we want to shard by like month going back in time, because our queries, we could take certain queries and just aim them at the specific shards that if we already knew what time zone it was. So we realized very quickly that we weren't going to come out with one indexing strategy. We were going to try a number of them and see how the different approaches to sharding would react when we had real user queries being run, and what was the performance impact of sharding, sort of equally distributed, a la mod 16 or mod 64, or if we did a date-time-based sharding. Probably one of the biggest things that we did, and I think that this approach is very much embraced in how SolrCloud works today, is we separated out the JVMs and the starting up of JVMs from the creation and loading of our cores. So at one point, we had 64 cores, right? 64 shards. And one of the things we were playing with is, hey, can we put all 64 shards on one server? Or do we want to put 4 shards on 16 different servers, right? In order to play around with that and be able to easily do that, we would start up our Solr processes, make sure that all of them came up, and when you're starting 64 JVMs, one of them's not going to start, right? You're going to have to go hunt it down and kill it and restart it again because something went crazy. And so, yeah, we would start up all our Solrs, make sure that everything was up and responsive and everything looked good, and then we used the Solr core admin to create those cores. And when we create them, we would tell them where the index was, and so if it was a brand new index that we didn't have any data in, we were creating empty ones. But if we already had that data out there, we would just pass the file system path to where that existing shard was and load them on. And that let us play around in many different ways with what was the right number of cores or right number of shards to have in a single JVM. And we had what we called our aggregator core, which was just an empty Solr core that had all the individual shards, their IP addresses, in there. So we could just query the aggregator core and it would go out to everybody. Which was great because that way our front-end application didn't have to have any knowledge of what was the current layout of what shards were running on which JVMs. So we did not do this quickly enough. So at this environment, right, when I started there, we had inherited all these old Sun, like big honking boxes with like 64 CPUs, 256 gigs of RAM. One had 512 gigs of RAM. It's like, wow, I've never worked with machines with so much capacity, right? And so we, in our initial ones, we like put the entire Solr, all the cores and indexes on one box. And we really didn't see great performance. And it was like, yeah, but there's plenty of RAM. The CPU is loafing along. Maybe there's something a little futzy about the I/O, but they're all attached to a SAN and everything else, and it wasn't really obvious. Eventually, though, fortunately, because one of the reasons we started parameterizing everything and being more flexible on how we loaded things was because we started thinking about, hey, we have all these extra boxes lying around that we're not using. Why are we trying to max out this one box? And so we started separating our shards out onto more boxes. Now, I can't tell you what the real problem was. We came up with this theory. Someone called it memory pressure. There was too much memory pressure on this one box, even though it had plenty of RAM. But what we did see was that when we went from, I think we started out from 1 box to 4 boxes, we saw a big jump in performance. When we went from 4 to 8 to 16, we saw a huge jump in performance. All our performance problems just disappeared. And so that was the value of being able to play around with what is the right architecture, because when we got up to 16, it was like, oh, wow, this is working really, really well. When we went wider, we started seeing slowdown. Now we're making so many HTTP connections out to so many shards, and it takes a while for them all to get back. Or if one of them just kind of gets bound up and we have a problem, there was sort of a limit on how wide you could go. But scaling horizontally was a really good decision to do, and we should have done it early. So what did we do for a pipeline? Well, one of the things that was really frustrating is why are there so many pipelines out there for ingesting data into your search index, right? And why does everybody feel the need to write their own? And how many people have written their own ingestion pipeline? Yeah, I mean, we constantly do this over and over. Well, we did a very, very simple pipeline. It was just a bunch of directories, numbered, right? Number 1, number 2, number 3, number 4, number 5, number 6, and then an error directory. And that actually worked out really well because we had these big data files that were out on a network-attached storage of some variety. And we would just use the move command. So we'd load up the file, do whatever content extraction, whatever other processing we need, MV it to the next directory, and then we had a bash script just constantly monitoring that, and when it saw that file show up, it would grab it. And if we were running, we'd be running multiple ingesters, and so they would try and grab it, and if they couldn't get it, then they knew somebody else had it, and they'd just grab the next one. So a very simple pipeline worked out really well for us. Although one of the things we quickly discovered, right, and this is, I think, a cardinal tenet of the whole big data world, is don't move your data around, right? You bring your code to the data. You don't bring your data to the code. In our initial ingestion process, we had like an ingestion server, and we'd throw all the files at it. We quickly realized it was going to take days and days and days to SCP all these files around. It was really painful. So we discovered that you don't want to move the data around. And we tried a number of different approaches to moving data around, right? Initially, we started out with SCPing files from the repository out to all the ingestion machines and then doing it. We looked at NFS, but discovered the problem with NFS shares. You have a single point of failure. We played around with a global file system, some clustered file systems, and they were awesome from the standpoint of you just had this single big bucket a la Amazon S3 or whatever that's globally available to all the boxes. But we had problems with if one of the boxes connected to this global file system started having problems, it would have what they called fencing, which would fence off nothing could change the underlying files until everything got sorted out. So tried a number of different approaches. We ended up using global file system for building our indexes because it worked well enough. But one of the things that we're really looking forward to is moving to something that's a little higher level, a little layer up, like using HDFS. So we're really excited about that. And also one of the things that we also ran into problems with is maintaining all our configuration files. We'd be moving those out. We had different indexes, different, pushing out all our ingestion logic and things. And what we started using was a Zookeeper as not just Zookeeper for the Solr, as a dependency to Solr to run SolrCloud, but we would put all our configuration information, all our artifacts into Zookeeper. So a jar file for doing content extraction, all the XML files or shell scripts, all of that would go into Zookeeper, kind of like a configuration management, kind of like a source code repository, but we'd stick them up there, and then all of our ingestion scripts and everything else would just ask Zookeeper, okay, I'm about to be run to do this job, give me all my data. And that was great because we could also send out updates to all our indexers using the Zookeeper infrastructure. So Zookeeper was really good for configuration management and keeping all the different boxes on the same page. So this was, obviously you can hear that we were playing around with a number of different models. We were changing things, we were playing with things. How do we know whether we were getting things better or worse? Right? JVM tuning is a black art. I think most people would agree with me on this. I think this was our final, like, hey, this is the best JVM tuning. Well, how did we do it? How many people recognize this, right? JConsole, right? We use JConsole extensively to do logging. One of the tips that I discovered is we had yet another shell script that would look at the properties file and find out the URLs to all the Solrs that were going to be run, and you can fire up JConsole and pass in all the endpoints that you want to monitor, so it pops up all the different windows. So we had one guy had like a big 30-inch monitor, and that's what we used to run all the. We had like at one time we had like 64 of these windows open everywhere because we had 64 JVMs we were monitoring. So early on we were like, okay, connect to server 1, connect to server 2, connect to server 3. Fortunately, there's a command line parameter that deals with that. And you can see here we've got like the nice sawtooth JVM pattern that we're looking for. We also use SolarMeter, right? How many people here have used SolarMeter? Yeah, it's a fantastic debugging tool for working with Solr, and it is bound directly into Solr, so it understands all the caches and everything else that are in Solr. You can see here we got a nice pretty diagram of the query result cache data, and you can tell when commits are happening in this diagram. So we use SolarMeter to kind of play around with, like, how often do we want to commit our data? How often do we want to do optimize? Is it worth optimizing our data set? That was one of the things that we figured out even on the 3x line, is that when our data was changing often enough, optimize just took so long, it really wasn't giving us anything. So SolarMeter was good, was great. So one of the things is we started using Solr as a key value cache. How many people went to Yannick's talk on Solr as a NoSQL, right? Isn't that great? I mean, there is some cool stuff in there. So one of the things that we discovered very quickly is in ingesting hundreds of millions of documents, we were using Tika. And Tika takes some variable amount of time, right? But it definitely takes some time, right? You know, even 10 milliseconds over hundreds of millions of documents means it's going to take a long time. And we were constantly, every time we'd rebuild the whole index, we would rerun all the ingestion process or content extraction. Why? There was no need to do it. So we were like, well, what are we going to do? Hey, wait, we have Solr. We already have it designed to work at large scale. And so we created a Solr core that had two fields, document path, document text, right? And we would throw all the data in there. And so our ingestion pipeline would query Solr and say, hey, do you have the text for this document? You do? Great. You don't? Oh, let me run the ingestion process and stick the results in there, right? And this was fantastic because you know, it drastically kicked up our performance. And we got thousands of queries per second on a single Solr, right? And this was before even the new stuff in Solr 4 that makes the Git much faster. We were just doing a select statement with a query, right? So Solr as a key value data store worked out really well. And we didn't have to go and get authorization to use Cassandra or CacheDB or some other tool. You know, our world was sort of Solr-centric, so let's use another tool that fits in really well. We started out with a really strong schema inside Solr, and we migrated to using Solr in a more schemaless model, right? And don't let anyone fool you, schemaless doesn't mean schemaless, it just means the schema is somewhere else. And the larger we were going and the more third-party applications that were pushing data in, you know, our schema basically moved into our ingestion model, right? And that created all the fields and named them and would stick them into Solr. And then this is probably the biggest lesson that we learned, right? Early on, someone had prototyped doing the content extraction by using Tika inside of Solr, right? The extracting request handler a la Solr Cell. And it worked, but it kept dying. And this one guy spent like days and days, weeks and weeks, hacking around with Tika and trying to catch out-of-memory errors and trying to catch just why sometimes you get a seg fault from the JVM and you know, you were killing Solr. And what we realized is that Solr was our bottleneck, right? Your search index is typically going to be your least scalable thing, right? And it already has so much work to do with ingesting data and building the index and serving up queries. Don't do expensive things. So it's great that you can prototype things, but if you're doing content extraction, do it outside of Solr. Do it out in your cloud of ingesters. The update request processor chain, which is a really, really cool feature in Solr that allows you to modify your incoming documents and put them, you get all the fields and you can create new fields or reformat fields or make calls to third-party web services from inside of Solr. Yeah, don't do it. Just because you can doesn't mean you should. So, look to move everything out of Solr, out of your search engine, because it's already got a big job to do. And then this was just my personal bugaboo. We were on the 3x line. We had one, maybe Solr 1.4 that had been sitting around as a demo. And then we added, oh yeah, that was it. So our key value cache was ginormous. I mean, nothing was indexed besides the ID, but all the raw text, like those 300 million documents, all the extracted text was in that thing. It was huge and a bear to deal with and a bear to move, so we didn't want to upgrade it. And honestly, there was no need to upgrade it. It did a great job. But then we were starting to play around with Solr 4 and other things, and so using Java binary was just a real pain. So, and we didn't see a huge performance benefit on it. So we were not fans of the Java binary format. Jarmageddon was Eric Hatcher's phrase once, that you've got all these conflicting jars because it drags a whole bunch along with you. Anyone played with Avro? It's really, okay, cool. At least some, yeah. It's a really cool Java binary serial, well, it's not a Java serialization format. It's just a binary serialization format. And so you can throw your documents into this Avro objects, and it stores the schema with it. So you can hand an Avro file off to something else, and it can query for what the schema is. And it gets parsed by C, Java, .NET, Python, Ruby, a whole bunch of things. And it's very, very compact and very, very fast to read. And so one of the things that we did is we did discover that updating that key value store was a little slower than we'd like when we were doing ingestion, content extraction. So we would just write out all the extracted content in .avro files. And later on, after we'd done the big build, we would slowly update the key value store. And the Avro file was just a really compact, small format for storing it. Could we have done XML? Sure. Could we have done JSON? Sure. We could have done a bunch of other things. But we were trying to minimize the amount of data space that it would take up. And these files, you could move them around, and the whole schema was in there. So if we had different versions of the content extraction, we could then just query the file, get the schema, and know what the data was that was inside of it. One other thing that we started playing with is using Tika as a pipeline. So everybody familiar with Tika? See the talk yesterday on it? So, you know, Tika extracts content. Well, it's got awesome auto-detect. So we started having multiple versions of the metadata file, and we weren't really sure what was in there. And so we first had sort of hard-coded, oh, I'll look in there and I'll make some binary decisions. We're looking at using Tika for all its auto-detection capabilities. It's a nice, fast SAX, doing SAX streaming, so it reduces our memory consumption. And the metadata structure that comes out of Tika is a key value, you know, it's a hash. It's a bunch of key and values, which is perfect for going into Solr. So, and it works with projects like Behemoth, which is a mother of a project. It's a big project that allows you to do machine learning and natural language processing in a Hadoop sort of environment. So we're optimistic that if we use Tika as our pipeline, we can then take this code and scale it out much larger using Hadoop and a Hadoop cluster. So this guy taught me something that I'd never realized until this project. You can upgrade a Lucene index from one version to another, and it's really easy. So that's the command that you run that takes an index from one version to another. So we did this a lot to prevent ourselves from having to rebuild the entire index. It was great for sort of testing and prototyping. At the time, we were evaluating SolrCloud, and so all the 4.0 stuff, and periodically Lucene would change under the covers, and it's like, oh, crap, we've got to re-index everything. So we just used this command to rebuild, to migrate our code. Worked out really, really well. And when it didn't work, you couldn't debug what went wrong. We were very big on making indexing as easy as possible. So, you know, so I don't know what the German equivalent of the Dollar Tree is, but you know, Dollar Tree in the United States, everything costs $1. The products are crappy, and nothing is going to last more than a week. At the other end, we have the Space Shuttle. Space Shuttle, every time you launched it, was $500 million to launch it, right? And you know, thousands of people all had to be at their A game, and everything had to be perfect or disaster happened. And in the middle, you have a brand like Target, which is a big superstore, where their products are nice and, you know, maybe not super high-end, but they're also going to last a little while, right? And I kind of think that that's where you want to get to with your indexing processes, right? We work with a lot of people who are like, oh, our index takes a month to build. I'm like, really? Well, what happens if something goes wrong and you got to rebuild your index? Or somebody wants to add a new field or try something new. They got to wait a month? So if you can make your indexing process sort of very rock solid, pretty easy to run, you don't require dedicated teams of people and thousands of servers to do it. I think this is an interesting challenge that we have, the emphasis on near real-time search. Near real-time search and big data don't go along with each other, right? I feel like there's a tension between the two. So I'm just throwing out a number, but it feels like if you have less than 10 million documents, you can do near real-time search very, very easy, right? It's just very easy to deal with. And if you have hundreds of millions of documents, you can make an argument that, hey, I'm going to add a document, and you might have to wait 6 hours until it shows up, or we're going to run big queries overnight, or there's other things you can do. And when you're between 10 million and hundreds of millions, that's a bad place where people want near real-time search. I'm hoping that this problem goes away with SolrCloud. I mean, that's what it's designed, partly what it's designed to do. But that's definitely a challenge that people want both huge amounts of data and it's got to be instantly reprocessable, instantly queryable. Anyone recognize what this is? What's that? HAL, excellent, excellent. So one of the things you can count on, and maybe this I should be in a cloud talk instead, is your servers will die. Your JVMs will crap out, Solr will blow up, bad things will happen. So we used to run a process that we called the Grim Reaper, who would go out and a couple of bash scripts would look at the log files, and he'd look and say, hey, wait, this guy's starting to run slower on average, right? And there was sort of a tipping point, and if he got too slow, kill -9, wipe that Solr out, and load balancer took him out of the pool, and it worked really well, and then he'd restart, right? And that was fantastic because it saved us lots and lots of 3 a.m. phone calls, and often the server would get slow not because of anything we did, right? Something happened in the network, right? Something happened in the environment that negatively impacted our Solr. So we had them in distributed locations, we just killed one and kept moving on. We had a lot of paranoia about someone accidentally doing a delete query that would like blow away the whole index, right? And nobody noticing that for a couple of days, like if it was over a long weekend. So we actually would run a delayed replication to a off-site data center every 3 days that would just get a copy of everything. And that way we could start, if worse came to worse, we knew what the index looked like 3 days ago, and then we could migrate it up. And it worked pretty well. You could do the same thing with rsync or other things, but it was very easy to test the quality of this index because you just go to it and query it and know that it was a good, viable backup. I posit that most people's backups, they have no idea if those backups actually run or not successfully, if you can recover or not. Big fans of the EnableDisable function inside of Solr. So really easy way to take something out. You can play with new settings, take it out of the load balancing pool, but still do queries against it. So that was in the ping request handler that allowed it. That's kind of what it looks like right there, right? So we would, so we would just enable and disable our Solrs, which would be great when you wanted to take one down and try out like new JVM settings. So you take it out and disable it, the load balancer would remove it, and then we do whatever testing we wanted to do. As I kind of mentioned earlier, provisioning, right? We quickly discovered that you need to automate your provisioning, right? You got to make it as easy as possible. What we want to do now is build actual VMs for all our base Solr cores and and be able to start them up. At the point in this project, we were running a bunch of like build type scripts, but it did make it easy to start out with, oh, I need 16, or I need 32, or I need a big one, I need a little one, making it really easy to set up environments. Now, one of the things that we discovered too, how many people have a traditional environment like this where you have dev, integration, and production, right? And production never it looks like dev, right? Because you say, oh, well, production has 100 servers. Okay, I need 100 servers, boss, in my dev environment. No, that's not going to happen, right? And so we had that same problem. And so we quickly started doing all development in our production environment because that's where all the boxes were, right? Our production environment, we were like, oh, it's still a prototype. It's not yet released. We're doing all of our stuff. But even after we were released, we were still doing development in production. We wanted, although we didn't successfully get it done, we talked about having a single pool, right? We want as many environments or as few environments as we want, right? We don't want 3. We want whatever we need, and it's up to the networking guys to make sure one environment doesn't step on the other one. And so in this sort of scenario, if we had more of a pooled environment, we could have 1 box for development because there's not much going on. We got 6 boxes for production because it's kind of a quiet time or that's what we need, and we're using all the other boxes to do load testing, right? So that's kind of the advantage of a pooled environment that's very flexible. And this is half of what cloud offers us. One other thing we quickly realized is, so we're building a index of all the patents in the United States, and the first time we built it, and this is just 1 million patents, it was 1 box for 5 days. And the second time we did it, it was 3 boxes, or 5 boxes for 3 days. And the third time we did it, it was 300 servers for 30 minutes, right? We could do this because we were using Amazon, and it was very easy to spin up all these extra capacity. But Amazon is expensive, right? It's not the cheapest solution. If you're working with, a lot of people have concerns about data and, firewall kind of issues. So one of the things that I'm kind of thinking about and been a fan on is most enterprise data centers, half the boxes at night are not doing anything, right? So starting to think about doing cycle scavenging, right? Anyone use SETI at home or something like that? That was, you're running an agent on your desktop at home, doing some processing, sending the results back, doing cycle scavenging. So we're interested in doing that for building our indexes, right? Because I'm taking 300 million documents and building an index. That doesn't happen every day. It doesn't happen every quarter, right? It probably happens once periodically, once in a long while. But when it happens, you need a whole lot of boxes. So we're looking at saying, hey, can we distribute a VM out to all these boxes that are not doing anything at night and building our indexes and then shutting them off when people come in or having a process monitor. So that's, I think that this is going to allow us to use more this is going to allow us to build big indexes in a more traditional data center environment where you have limited number of boxes compared to in the cloud environment. So, failover, you don't need failover, you just need a pool of resources and you can expect something to die. So this is probably one of the bigger lessons I learned out of this project is the more data you have, the harder it is to figure out what's going on. And one of the things that we're hacking on is what we call Solar Panel, which is trying to better visualize. So we did some work with Zappos to try and figure out, if you go to Zappos and search for dress pants, right? Or no, dress shoes, you would expect, black shoes to come up. And it used to come up with that. But today, now that they have so much more data, and now they sell not just shoes, but other articles of clothing. When you search for dress shoes, you get back both dresses and shoes. So they've actually fixed it for dress space shoes, but if you do any kind of dress space shoes or anything else like that, you'll get back a weird data set. So thank you. In the couple of other sessions I've seen, people have been nervous about asking questions. So if you don't want to ask a question now, please hit me up on email or Twitter or whatever. So. Thank you. Good question. So how do you handle failures in the pipeline? So one of the things is that was a constant problem. And I don't think we ever really solved it well, right? Because we had to make sure that every single last document went in. And our queue that came out, we had to make sure that if a delete happened, if a document went in and then a delete command came out, that when we did the ingestion process and saw, hey, delete this document from our index, that didn't happen before an ingestion happened. We put stuff into an error queue, and we retried things a lot. And we would track like the timestamp of when anything went in, and then we would look for, if we were building a full index, we would look for, when we finished building an index, each chunk of an index, we would then go and look at the original source data and make sure the counts matched up. And if it didn't, then we'd throw that away. In fact, one of the things that we were playing around with was building out lots of small shards, right? 1 core per sort of data file. And as long as everything looked perfect, then we would merge it into our main index. But if anything didn't, then we'd just start over again. So we definitely had some of the, I don't know what went wrong, so I'm just going to try it again. And do that on sort of data file by data file, building a small Lucene index, and then merging that in. So yeah, so looking at your queries, that was one of the things is the team I was working with was sort of your traditional developer team, which meant they didn't want to look at what the users were doing, didn't want the users to bother them with their complex queries or their problems. And so one of the things that we did was some analytics around what were the queries and what percentage of the queries actually had like a date time range, right? Show me all the documents that match this within the last whatever time period, right? And one of the things that we did discover is that a lot of people were interested in things that had happened in the last 2 days. And that was documents that had been ingested in the last 2 days. So one of the things that we looked at was having a separate index that was just for that time range. And it was probably like 40% of the queries were just that small date range. And so it was actually worth having a separate index. That's an ongoing project to kind of set that up. But that would give us a much smaller index. We were balancing against that, though, the challenge of, okay, now we've got 2 indexes. We were calling them, we had some sort of phrase along the lines of special built or special purpose indexes. But then that meant our ingestion pipeline had to be smarter about where do the documents go and, oh, I need to look at this document. And if it's newer than this timestamp, send it to this index. Otherwise, send it to the main one. So. But looking at the user queries definitely taught us a lot about what we needed to, what our caches had to look like and what fields and things like that. Okay, how do you analyze the user queries? I mean, it's not the worst tool in the world to throw them all into an Excel spreadsheet and split them up by query fields and things like that. That's not a bad start. A couple of things that we did was, one is we would take like a day's worth of user queries and dump that into a single file and run it through SolarMeter. So SolarMeter can just read in a set of queries and just blindly run them. That was really good for taking real user load and seeing what the impact was on our cache hits and other things without waiting a day. I don't feel like it's a solved problem, though, of looking at user queries, right? We definitely would look at user queries and figure out, okay, what date ranges were people looking at or what fields were people looking at. And also we found out that we were doing a lot of faceting. We would look at all the queries and see what the facet fields were, and then actually go and talk to the application developers. And often they were querying for facets that they were never using in the application. They sort of had sort of a blind service that would just, blindly facet on a whole bunch of fields. And so we were like, okay, hey, can we not do these things because that'll help reduce some of the load. So, but yeah, I don't really have a magic solution for the analytics. It's just basic, put in a database table or on a Solr and make queries against it. So, cycle scavenging was interesting. What are you using? Don't have a solution yet. We're playing around with Condor. Condor, which is in the slide, the Condor project, seems to be the most widely deployed cycle scavenging tool. But it's definitely like you install it on the box and then give it whatever you want to run. We don't really have a solution yet. That's kind of an ongoing R&D effort. It may be as simple as running VirtualBox or that type of thing and being able to push that out, or whatever your JVM thing is, monitoring it and then killing it. So I think the approach has a lot to offer, but it's not packaged up as a solution. But I'd love to talk more about it with anyone else who wants to help me do it. So, well, thank you very much. I really appreciate your time, and I'll be around, so I'd love to talk to you more. So thank you.